Hello and welcome to Bay College's online lecture videos for Intermediate Algebra, Math 105. Today we're going to look at section 6.7, which deals with multiplying and dividing within the complex number system, or with complex numbers. And honestly, we're not going to spend too much time reviewing multiplication and division, because at this point in your algebra you really know it very well. It should be second nature. But what's different here is when it comes to the complex numbers, when we do operations such as multiplication and division, sometimes there's a step that we have to do prior to actually doing the operation. When it comes to multiplying, the first thing we need to do is factor out those units of I. All right, if you recall when we had negative or under a square root, we could always factor out that square root of -1, call it that I value. That's the first thing we do before we do any multiplication. Let's put this into an a plus bi form. Well, if we do that here, I can factor out that -1, and we call it the square root of 2i. And we're going to multiply that by the square root of -7. Well, that's the square root of 7i. Just pull out that -1, call it I. It's under a radical, so that's what it is. And now we can see, okay, well now we can multiply it. If we think of this as being maybe 2x and 7x, we would get 14x's squared. Well, we're going to do the same thing here with radicals. The square root of 2 times the square root of 7 is the square root of 14, because they both have the same index of 2. And I times I is I squared. And if we recall from the previous section, 6.6, we know how to deal with these powers of I. I squared is -1. Well, -14 times -1, well, that's just going to change its sign. We get negative square root of 14. Now, this is why it's very important to factor out that I first. If you recall your rules of radicals, well, if they have the same index, you can just multiply them together. -2 times -7 is positive 14. This would be the square root of 14. Well, the true answer in the complex number system is negative square root of 14. Which is not the same number as positive square root of 14. So we have to deal with that I first. Take those I values out, and then do the math like you would normally, multiply, right? All right, let's move over here and look at another example. Now, we've multiplied binomials before. Well, we can do the same thing with the imaginary unit. If we look at this, this is an imaginary number where we have an A value and a B value times that I. And we have an A value, and our B value here is 1 times I, so it's just like a binomial, but it's complex numbers. Well, we can treat them like we did with polynomials. We can use that process of FOIL in this example. First over and last. We're just using the distributive property. So let's go ahead and do that. 7 times 3 is 21. 7 times I is 7i. -4i times 3 is -12i. And -4i times I is -4i squared. Now we have to do what we've always done, combine like terms, but we see that I squared. We also have to deal with that. Well, let's take it one step at a time here. 7i minus 12i, we're just combining those imaginary units, and we get -5i, -4i squared. Well, what is I squared? If we recall, I squared is -1. -1 times 4 just changes its sign. It becomes +4. Now that we've dealt with that, we notice we have more like terms, don't we? We have 21 and 4, which is 25 minus 5i. When multiplying or dividing complex numbers, we always want our last answer, our end answer, to be in a plus bi form. A plus bi. And if we compare these two, we can see 25 is my a value, and -5 is the coefficient of the I term. So this is our goal each and every time. Well, what if we want to divide? Well, when we divide by a complex number, we have to realize a complex number contains a radical. And if we're dividing by radicals, we always want to rationalize the denominator. And if we recall, we worked with something called conjugates in order to rationalize denominators. Well, a conjugate is just that number or set of numbers with an opposite sign in there. So when we do that, we actually have the sum and difference of terms. Well, when we FOIL these out, the middle term always cancels because we end up with the difference of squares. hopefully we remember the difference of squares and being able to factor the difference of squares into the positives and negatives of those numbers, the square roots of those numbers. Well, a complex conjugate is the exact same thing. We have a plus bi, our imaginary number, and we have a minus bi. So instead of giving this a new name, it's just a complex conjugate. That's all it is. And if we multiply this out using FOIL, like we did in the previous example, we'd get a plus bi negative a bi. Those middle terms are going to cancel out, leaving me the first term squared, just like it did here, and the last term squared, minus the last term squared. Let's show this then. Minus b squared, I squared. What is I squared? That's negative 1. That's going to change that sign. I squared is negative 1. Negative 1 times negative b squared is a squared plus b squared. Now, hopefully maybe you'll make that connection. This, when we saw polynomials like this, we said, well, that's prime, it doesn't factor. Well, it actually does factor in the complex number system. But that's an aside there. Let's just look at this and say, how can we use this when we're dividing? The complex conjugate is what we use to rationalize denominators. So if we're dividing by imaginary numbers, we have to always remember we can't leave a radical in the denominator. And this I is a radical at our imaginary unit. So we can rationalize this denominator by multiplying by the complex conjugate. Well, that's this with a negative or opposite sign to that complex number. These are complex conjugates. But we have to remember what I do to the bottom of a fraction, I have to do to the top. What I do to the denominator, I have to do to the numerator, so I don't change its value. If we look at that, that's just some number divided by itself, which is 1. So we're not changing its value. So now we have to FOIL on the bottom, FOIL on the top. Well, this really doesn't require FOILing because it is a conjugate. In this case, a complex conjugate. But when you multiply conjugates, you get the first term squared minus the last term squared. Well, and that requires a little bit of simplification because we have an I squared, which is just negative 1. Negative 1 times negative 9 is positive 9. 4 and 9 is 13. No more radical in the denominator. No more complex number in the denominator. 13 is a real number. And now, if we do the same to the top, we're going to FOIL this out, and I'm going to get 4 minus 6i minus 6i plus 9i squared. That's just using FOIL. Combine some like terms. Well, these two terms here are negative 12i. And this I squared, or 9i squared, becomes negative 9. Now, if we combine our like terms, I have 4 minus 9 is negative 5, our real value, the real part of the number, the a, and minus 12i, our imaginary portion. Now, is this in a plus bi form? No. The numerator is, but it has to incorporate the denominator. And if we recall from the previous section when we talked about adding and subtracting complex numbers, well, this we can just split up. So if we split it up, we get negative 5 13ths, let's clean that number up a bit, minus 12 13ths I. Both of these are divided by 13, so I just rewrite them. Now it's in a plus bi form, where a is negative 5 13ths and the coefficient of the I, negative 12 13ths, our b value. Let's look at this example here. Now, this is a pure imaginary number. It doesn't have an a portion. Our a is actually 0. So I could think of this being this way, a plus bi form. Well, this is essentially 0 plus 3i. Its conjugate would be 0 minus 3i. So if I can multiply by its conjugate, I could put minus 3i here. But because it's a pure imaginary number, and I know eventually we're going to have to reduce, we always have to reduce fractions, because that's what this is. Every pure imaginary number complex is just changing the sign. So I'm going to put negative I. The coefficient really doesn't matter here. Its conjugate is that I term. That's the radical we want to eliminate. So this will help you keep your numbers a little bit smaller. You could use negative 3i You'll just have to reduce more when you get towards the end. So what I do to the bottom, I do to the top. And this I just have to multiply. 3i times negative I is negative 3i squared. And hopefully we see right away, well, that I squared is just going to change that sign, isn't it? And then here we just have to use the distributive property. Negative I times 2 is negative 2i. Negative I times negative 3i is negative 3i squared. Now I hope you don't think we can cancel these, because you cannot, right? You can only cancel factors. These are terms. So be very careful there. Now, I know I switched the order there, but it's because I intuitively know that when I take care of these I squareds, we're actually going to have real numbers, because I squared just changes the sign. So I squared here changes that negative to a positive, minus 2i, and I squared changes that negative to a positive over 3. Now if you notice here, we're almost in the home stretch here. We have to put it in a plus bi form, so I'm just going to split it up just like we did the previous example. 3 over 3 is 1. And negative 2i over 3, negative 2/3 I. Now it's in a plus bi form. Hopefully I didn't make any sign errors, but that's it. We've reached our goal, a plus bi. This has been section 6.7. Thank you for watching.